Okay. Let's do a bit of social media. Start this stream off. It's a new week today, Monday morning. What's the date? Monday the 3rd of March. Okay. Get rid of all these. Put a little bit of music on. Where are we? All right. So today, well, let's do the intro. Hey everyone, Lazy Ben. So today, we're going to continue with rigid body physics. It's going to be part of a mining system, mining for resources, eventually. But right now, we're just working on getting some physics together because I want to be able to shoot rocks with a laser and have the rocks break apart. And right now there's no physics in the engine, so, well, there's a cloth, and that's all we've got. So we did start last Thursday, last hour or so of the stream, looking at some old rigid body physics code that I had. We implemented collision detection, GJK collision detection, which is a pretty standard form of collision detection for 2 and 3D games. And we made something called a rigid body, and then we implemented simulate pair, which doesn't do the simulation, it just does the collision detection at the moment in a fixed time step. So it just does the intersection of the collision detection. Collision detection is 2 parts usually. It's intersection testing and then intersection response. We haven't done the response bit. So the response is what happens when an intersection is detected. What do you do? Because you can't just leave the item or leave the entity colliding. You need to actually respond to the collision. So I think the first thing we're going to do is look at how that is implemented. Okay, so we have this little helper, this little test function, and all this does is it just detects that the intersection between 2 rectangles at the moment and draws if they intersect. So let's just run that. So you see it's a green rectangle, and if it goes into this yellow one, it goes red. So that's GJK collision detection. It's colliding. It's not colliding. So now we need to do response. What happens when that happens? What do we do? Right, we obviously have to like tilt the red rectangle, rotate it and fit it up against here. Fit it up against the yellow rectangle. Alright. So let's bring back up my old collision detection code. My old rigid body code, sorry. So we've basically just ported this over So the next step, where are we? Still a lot to do. So we've written this bit. So that's the intersection. And then we need to write the resolve bit. So what do we do if we've detected an intersection? It looks like it's broken up into two separate occurrences, here and here. So this is obviously if we're actually in intersection. We do this, and this is if we're going to intersect before the next frame, because with good collision detection, you don't just test when you've intersected. You test if you're about to intersect as well, because what that means is if something is moving very, very fast, you don't want it to get up to the object. It's not intersecting it yet, and it doesn't intersect, and then it's going so fast that it passes through the object by the next frame, and then you do a test and it's still not intersected, and then you get the really fast object will just like fly through what it's meant to collide against. So you're gonna have to test if it's going to intersect as well in the future. Right, but we'll do that later. Right now we're just gonna do this. What happens if we have detected that it is intersecting? And we do this thing called EPA find penetration. I'm not even sure what EPA stands for. The expanding polytype algorithm. Right. So it's looking at penetration depth. So this is how far we've intersected, because obviously we need to know where we've intersected on the shape, how far, so we can push the objects apart again. Because collision response usually is pushing objects apart, so because you don't want them to intersect. So this is all about pushing the objects apart. Alright. So let's implement expanding polytype algorithm. I mean, we don't have to implement it because I've already implemented it, but we need to port this over. Alright then. So what I want to do, let's try and see if we can, oops, I want to put this on a different desktop. I think that works. Okay. That's me flicking between the desktops there. Okay, so let's go back to GJK, right? And then we do simulate pair internal. So the next thing we need to do is EPA find penetration, which is a very nice function name. And it returns an EPA penetration result. Normal depth succeeded. Okay. So we might just do this straight up in here. So struct EPA penetration result vec2 normal float depth bool result. And then we'll make it part of this in case we want to use this later on its own. So EPA find penetration. Okay. Two rigid bodies and a simplex. That's what it needs. Probably don't need to mess about with the rigid bodies. Or the simplex. Well, the simplex is in here. If we're not passing the simplex, should this be public? So I might say we do pass the simplex. I think what we're going to do is make this private. Because obviously this depends on the simplex, and the simplex is created when you call simulate pair. So it assumes that you've called simulated pair first, which I'll definitely forget to do if we make this public. Alright. So what does EPA find penetration look like? Create expanding simplex. Get simplex winding. So it needs to determine which direction the simplex is winding. Yeah. Clockwise, counterclockwise. So it creates an expanding simplex based on the simplex, which is its winding and the edges. Wow, this is complicated. It's alright though. Right. So we want an expanding simplex. And then create expanding simplex. Which has just got the simplex in it. So I wonder if we could just have like an expand. Nah, we'll do it. Const simplex. So what is an expanding simplex? It just tells you the winding of the simplex and the edge. So we're creating a series of points into kind of like a mesh. Interesting. Alright, so I want P1, P2 and normal. So expanding simplex edge. So it's P0, P1, whoops, normal, and distance. So it creates an expanding simplex. So let's just copy this. It calls get simplex winding. Let's just determine which way round the simplex is. And then it goes from I0 to 0, 1 and 2. Okay. So the expanding simplex here has an array of edges. I don't know if it needs that because Aaron, thanks for the follow. Got any questions, and just let me know. Just working on physics stuff. Just looking over some old code, porting it into the new engine. Oh, awesome! Yeah, great. Oh, fantastic! Yeah. Let me know what it is, and I'll check it out. So I'm working on a bit of physics because I'm going to do mining in the game, and I want to be able to blast rocks apart. Yeah, awesome. I'll check it out. Oh, nice. Mind if I show it on the stream? I won't just automatically show it on the stream if you don't want me to. Yeah, looks really nice, man. Oh, cool. Quantum computing, wow. That's cutting edge stuff. Ontario from Canada. Awesome. Nice one. Yeah, good luck. The particle project. Oh, I see, yeah, okay. Yeah. Yeah, awesome. I'm not going to do anything quite as crazy as this. I just want like 10 particles, I suppose. 10 meshes to break apart. Well, one mesh to break into 10 meshes to then fall apart. Say if you're shooting a rock, just want it to break apart in a nice way. Yeah, awesome. Yeah, so I'm just going over some rigid. I wrote some rigid body code quite a long time ago, maybe like 5 or 6 years ago. I'm just refreshing my brain. This is old code, this. And I'm just refreshing it, so I'm doing a bit of a port. Oh, no problem. Right then. So, what were we doing? Trying to get the winding. Now I was saying I don't know if we need to allocate stuff because it's a fixed number of. It's only 3 or 4. There's 3 edges. All right. So get simplex winding. So we're just determining which way around the simplex is. It returns an integer. It used to. I think. I might just do it here. No, let's just do it. Let's keep it in here for now. So it probably needs to be above there because I think it needs a winding. Say unknown clockwise, counterclockwise. All right. So that's what we're doing. So static is simplex winding. Get winding. Have a quick look how we did this. So we're going through the simplex. So for we might say yeah, that's probably fine. For I to array count simplex points. I'm going to work out the next one. So J is the next one. If the next one's 3, say if the next one's count and we set it to 0, else we just send it to the next one. And then we need cross 2. We don't think we have cross 2. So auto A equals simplex points I. Auto B is simplex points J. And then we need cross 2, which we don't have. What is cross 2? Oh, we might have that. Find out. Got cross 4. No, we'll put it after dot. So that's just that. So auto cross equals A cross B. If cross is greater than 0, return counterclockwise. Else, if cross is less than 0, return clockwise. If it is 0, for every case, we return unknown. Okay. All right. So it's expanding simplex. Okay, so now we can get the winding. So we just say dot winding is get winding simplex. All right. So presuming if we don't have winding, we can't do it. So if we can't do it, this kind of needs to be optional. So we say if winding is less than 0, that's confusing. Ah, right. So if it's clockwise. Yeah, this is confusing. So we say we can do it if we don't know the winding. I'm not sure that's correct. Right, we'll stick with the pot. Zion 19. Thanks. Yeah, if you've got any questions, just ask. I'm just porting over some rigid body physics code that I wrote a few years ago. I'm trying to just refresh my memory and get it into this engine because it doesn't have any rigid body physics. With the goal of I'm putting mining in the game, so I want rocks to be able to break apart in a semi realistic way. Not, yeah, this is my own engine. Yeah, that's right. So I'm actually working on gameplay really at the moment. So I'm trying to make a game with the engine. So the engine's kind of in a state where I can make a game. Except this physics thing really. I've got a bit of physics. So I was looking at the cloth. This is the cloth physics that I have. But not really much. Alright, cool, yeah. I'm by no means an expert in this. I've written it before, but it was about 5 or 6 years ago. And it worked then. So I'm just trying to get it to a point where it works. A little bit. Alright. So, where were we? So we get the expanding, so we get the winding. And then we're going through and we're just basically setting the edges and calculating the normals. That's straightforward. All right. Yeah, I have that somewhere. Where is it? There you go. It's commented out now. And there's the 9.8 times by the time step. Oh, let's ban this bot, hang on. That definitely makes things fall down. Exactly, yeah. I know. If it wasn't for apples, we wouldn't have gravity. Because the apple needed to fall on his head for gravity to exist, right? Alright. Where were we then? We were down here somewhere. Okay, yeah. So all we're doing is we're just going through the shape and we're setting the normal and the edges. I think Newton was more romantic than that. When he wrote in his diary, it could have happened that way. And then he was like, I can't, for all of eternity, that can't be what I'm remembered for. Alright. So if we're already going through it, we could probably just calculate the normal right here, right? Right. So let's just see what this does. This is for every edge. So these 2 points here are the edge. So we get the clock, we get the direction there. So that bit goes in here. And that bit goes in here. And then this bit is for all of it, for the entire edge. Okay. So -1 was the state where it was clockwise in the old engine. Okay. So instead, let's just put this here. And this is result.winding. There, oops. There and there. I'm just concerned why we were allocating them here. I want to check that we're not allocating them anywhere else, because oh, we are expanding it. So we do need it to be able to allocate more. That's fine. Yeah, expanding it, hence its name. Okay, so we want an array of expanding simplex edges. Okay. Yeah. So initialize, what does initialize do? It just calculates the normal and the distance. All right. So we're going to do result.edges in place expanding simplex edge. That's not right because we've already got the normal there. Oh yeah, the normal, so we missed that line off. So the normal is 0.2, 0.1, 0.2, 0.1. So that's 0.2 minus 0.1. Which is just B minus A in this case. I think so. So we got dot normal equals normal dot x normal dot y minus normal dot x. And then this is result dot edges dot in place expanding simplex edge dot normal equals vec2 minus normal dot x minus normal dot y normal dot x. Okay. And that gives us an index to look into. And then we can say if index so that's both dot normalize, right? Well, this is normalized. And then result edges index distance is the absolute value of 0.1. That's where the point, so that's A dot normal and then result edges index dot p0 equals A, and then p1 is B. So that creates the expanding simplex. Barring typos and compile errors. Alright then, great. See if that builds. That builds alright. Okay, so we've done this step now. So what I'm going to do is just copy this all over. So just going to go results, return the result, and then we're going to go auto expanding, well, exp simplex equals create expanding simplex from the simplex that we already have. And I might just step through this. Because that's obviously, we've changed quite a bit there when we ported it over. I'm going to check it's right. So we can get rid of get winding. So we can go if intersects what do we call it? Create expanding simplex, or no, it's EPA find penetration. A, B. Okay then, so we'll just fire a breakpoint. We'll build all this up and then we'll see if it is making the right shape. And draw it if we want to. Might be easy to draw it. Draw the simplex out. Might be quite a big build this because we changed the maths library to put the cross product in of the 2D cross product. And obviously everything uses the maths library, pretty much. So obviously means if we can't create the expanding simplex here, we can't run the simulation. So this should also probably be an optional, like it might not succeed. Doesn't succeed if we haven't put any edges in to the simplex. Benkley, hey, how's it going? I'm doing well, thanks. We're on to physics today. Rigid body physics coding. Quite exciting. Did you have a good weekend? Glad you're doing well. Alright. So we bring it in. We have our simplex points. So what I think I might do is draw this. Draw the simplex and the expanding simplex. Well, just draw the expanding simplex out. Which is straightforward. So this is just a bit of a debug thing. I'm going to get the canvas. One of the things I might have to change is that when we draw this, because they might be drawn over the top of this, we'll just say -1. So we want this to be drawn behind what we're about to just draw. We're going to go for auto point. Oh, good. I'm glad you had a good weekend, Benkley. It's really sunny here. It's really nice. It's like spring is starting, hopefully. Edges. So that's an edge. I'm just going to go canvas.draw line in world edge.p0 edge.p1 float color. We'll draw them white in max, and then we don't want to draw the normal. The normal's just a direction, so we need an actual so we'll draw it n0 equals e dot p0 plus e dot p1 minus e dot p0 times 0.5. So that's like halfway up the line. And n1 equals n0 plus E dot normal. Maybe. It doesn't matter, we'll just draw it. Canvas dot draw line in world. Then not. Then 1. And we'll just say draw this blue in max. Okay. Doesn't know about game canvas. Oh, so it's in well, just include the game, and then we'll do get game dot get game canvas. We'll do it that way. Okay. Draw a line in world. See what this looks like. So I don't know if you can see the blue. The normals are right. The normals are the blue. I just wanted to check the normals. Oh, I can't. I'm going to draw it a different colour other than blue because blue's a bit difficult to see. Just draw it green. Yeah, the normals are right, the edges are right. Alright, so I'm happy we can move on. So this is 100 iterations, plumbing heck. Or up to 100 iterations. Alright, well we'll just go with this anyway. That's a lot of iterations. So get closest edge in the expanding simplex. Get closest edge. What is that? Closest position along line to origin. So it's the closest edge to the origin. Closest position along line to origin. Do I have that? Anything like that in the maths library? Find closest edge to point. That's not quite right because that returns the edge. And we're wanting to return the position. Alright, we'll put that in then. All right. Don't know what. Let's just put this in here for now. Oh, we've got it right there. We'll just do that. So we'll just lock this to Vec2. That's totally fine. I don't think we're going to be wanting to do it on anything but Vec2. We're in a namespace here. Not really. Alright. So it's AB dot AB. So that's AB dot length squared. What do we have to find to be small float? Yeah, that's fine. Put that there, that's fine. Clamp 01F. Okay, good. Let's just check that builds. Dot not found. Oh, it's AO dot AB. Whoops. Okay, so we're going through 100 iterations. Closest edge, get the Minkowski difference, dot product. Expand, expanding simplex. So we might not do all 100 iterations. We're giving it 100 chances to succeed. Okay. So while iter count minus minus is greater than 0, get the closest edge in the expanding simplex. Okay. So we're just going to go optref expanding simplex edge, get closest edge to origin. Okay. So we're just looking for the minimum distance between all the edges. So auto dmin equals the maximum. Well, we'll do it this way. And then for auto e in edges, auto pd equals closest position along line to origin, e.p0, e.p1. Then we want, we're dotting it to find the length squared. It's undefined, it says. I think it's fine. L equals PD length squared. Well, yeah, auto L equals PD dot length squared. So why isn't this working? Needs an L value. All right, yeah, sorry about that. Closest position along line to origin could not be found. It is in a namespace in geometry. So this is just geometry. Okay, so we'll just call this D. If D is less than D min, then we have the closest. So D min is D, and the result equals E. Okay. Now if we're growing this, we have to be careful that we don't store the... Yeah, I think we're going to change this because these edges are going to increase, so I don't want to be returning to references really. It assumes you have edges as well, that's the problem. Alright, this can be optional. Alright. Okay, so this is edges E. Okay. So we're actually here in the... We're actually taking a pointer here, which we don't want to do. So this is edge index. Edge index equals exp simplex dot get closest edge to origin if not edge, break, because we just cannot, there's no edges, so we can't keep going. So we get the Minkowski difference. Point equals get Minkowski difference between the rigid bodies A and B with EXP simplex dot edges edge index, and then we project it onto the normal. Dot. Okay, let's cache the edge. Yeah, with the edge. We say if projection minus edge distance is less than the small float, we're there. Result dot depth is the projection. Result dot succeeded. Well, maybe we don't need that. Result dot result. Well, I'll call it succeeded. We might not need that. It's true. And then we break. Else we try again. We expand this. We expand the simplex and we try it again. We add it in. So we create expanding simplex. So the expanding simplex we need expand with a point. All right. So if we didn't succeed, we expand it. So exp simplex.expand, passing in this point that we've just created. Destroy expanding simplex. I mean, that's just gonna get destroyed anyway. Alright, so then we say if not result dot succeeded, so we couldn't find one. And we need an edge. If edge index point and the normal. So I think this is standard optional. And we remove succeeded. Optional EPA penetration result. And this is just and there is a result and not a result. If there's an edge index but we don't have a result, then we do that. And then we call destroy expanding symptoms. Probably just freeze the array. Yeah, so we don't need to do that here. All right. Okay, so these need to be, we need to be Minkowski difference for 2 points rather than 2 rigid bodies. No, that's not right. Edge. It's the edge normal. Dot P. And we had dot product in there with the normal as well. Okay. So we just need to implement this expand here. So auto closest equals get closest edge to origin. If not closest, return. And then we free the closest off. So we want to do edges dot order remove closest and then we create two more edges. All right. So I wonder, so it, with the risk of rewriting some code here, I should write a constructor for this. She needs 2 points and a normal. P0 is P0, P1 is P1, normal is normal, and distance is that. Where were we? We'll do that. So this just becomes A, B, vec2 normal.y minus normal.x. And stick that straight in there like that. And this becomes minus normal.y normal.x. And then winding can be calculated in here as well. So the winding is A cross B. It's greater than naught. It's counterclockwise. Well, that's, yeah, the winding's not stored in there anyway, so that's okay. And then we can get rid of that. That means index is not a thing anymore. And then when we create new edges, we've got closest on the new edge, closest and P being the one we've got given. So we want to do edges dot in place closest so we want to do auto closest equals edges closest, and that's a copy. So we want to do copy dot p0 p winding edges dot in place not closest. So why have we got winding there? Initialize expanding simplest edge. Right. No. It's to tell it what direction if winding is counterclockwise, else if winding is clockwise. Okay. So if winding is less than 0, so we're back to here again. So it's P to 0.2. Else the normal is that. So let's check that compiles. Edge undeclared identifier. I'm not sure about that. Because it's a new normal. It's not the old normal. So this is what I think. I think what we do is we don't pass the normal. We just do it all in here. To be safe. So this is P0 minus P1. P1 minus P0 normalize. And then we're just going to go, I'm going to go auto N, and then I'm going to cross them, which we do. we swap the normal over. We do that. And we do the distance. Okay. So this is just edges dot in place result dot edges dot in place AB. And then we can set the winding result.winding I'll just leave it. We'll just leave it. It's fine. So we'll say result that edges in place AB, and then we'll just set the winding separately for now. And then here, this makes this a lot simpler because we don't need the normal. We don't need to worry about winding. All right. So if we get this compiling, then we'll take a quick break. And then we shall resume. All right, quick break. Back in 2 minutes. Alright, I'm back. So now we've changed the way we generate this simplex, expanding simplex. Let's just look at the debug out drawing and see if it's still right. So we might need to keep that. We could just say get winding. So why do we need that in the first place? So we might not need this. Let it build. Once it's built, I'll just check that the drawing is still the same, now that we've changed stuff a little bit. And then I think that's everything. We've got the normal and we've got the penetration depth. So we can draw that out and see if that works. Obviously we don't have the point of penetration on the shape, which we maybe need. Alright, okay. So that's still drawing, that's still good, that's worked very well. Okay, and we are expanding it now. So let's see if we get this. Alright, so what we might do is draw this closest edge to origin. So auto canvas, get game canvas, as your canvas draw line in world. Do it here, I'll make a copy of it. Copy p0 copy.p1, and then we should say float color int max. Just draw this. Should probably draw the world origin as well. Draw circle in world. We'll just draw that white. So that's drawing the origin point. Segment count 16, I'll be fine. That kind of looks wrong to me. That's definitely the closest. If you move this over here, that definitely goes to be the closest. It's drawing another... The line is wrong though. And now they're all the closest. Well, actually it's drawing it multiple times, isn't it? It's doing multiple loops. Okay, so let's just take this out. Let's test it here. Simplex x simplex dot get closest point to origin. Oops. And then we're just going to go auto copy edges, edge index, and then we're just going to go if edge index. So we're just doing it once per frame there. Don't need two ifs. All right. See how it's going pink? If it's getting close, the origin's the white circle there. No, we don't see it. The origin's the white circle in the middle of the triangle. So that is working. So what didn't work was when we drew the expanding simplex. So let's just draw the simplex right at the end. Ooh, yeah, no, that kind of looks like it's working. Try and get to expand. It's not expanding very much. It's only expanding a couple of times before it's... All them normals look right. All them edges look right. Maybe, yeah. All right. Okay. So I'm going to say tentatively that is working. Fine penetration is working. So let's just quickly draw the penetration. We don't know exactly where to draw it. We can draw it at from the center of rigid body A. So we're just going to go. So we've got a normal and a depth. So we're going to say canvas, draw a line in world. I'm going to go from a.bounds.center to a.bounds.center plus result normal times result depth. And we'll just draw this. We'll draw this white as well. See what that looks like. Can't see it. What contrasts yellow? What we might do is that big yellow thing, a big yellow square. We'll just give it some alpha. I think it got the penetration direction right though. That looks good. So see how it gets longer as the more we go into the, and the direction is possibly pointing into the, probably needs to point out of it. So if we just, well, let's just see if depth is negative first. Depth is not negative, so I think if we just do times by -1, to check that, I mean, obviously we don't have where on the shape it's penetrated yet. That seems good though. So the idea is we would push that red square along that white line to get it out of the shape. So if we do we do something like a.bounds xy plus equals result normal times result dot depth times -1. Let's see what that looks like. No, plus equals. Really? All right. Oh, it's something else. Oh, it's because it's constant. So what we'll do... we'll just say auto P is that, and then we'll just do canvas draw quad in world rect P a.bounds.width height float color, I think it was green. Int max. Alright, how's it going? Nice one. Yeah, I'm doing some physics.
Hey?
I'm doing some physics programming.
Doing some physics programming?
Yeah, for the game. Look at that. You see how the green one stays now on the edge of the square. So it's being pushed back out again.
What are you doing?
I'm doing collision detection. So this yellow square, you can't go. The green square can't go inside that yellow square.
Uh-huh.
So if I move it towards it, you see how it keeps it on the outside.
Yeah.
So the red square's where it would be, and the green square's like
Where it rebounds to.
yeah, where it's been pushed out to.
That's clever.
Yeah. Yep.
Do you eat tea?
No, I'm okay, thank you. I've got coffee. Alright. And obviously it flicks to different sides because we would be pushing it back there. Alright, good. That's a good good result, that. Alright, check that in. What's the next stage? So we've found the penetration point. We can get rid of this because we don't need it, I don't think. So we find the penetration. And then we do something called resolve collision. So while we're intersecting, we're pushing them apart. Proportional to mass. This is where a bit of the rigid body stuff comes in now. Why are we doing that? Oh look, we're calling evaluate there. GJK separation result. So what is that? So that's on time of impact. We haven't implemented that yet. So all this is doing is just pushing it based on mass. Pushing both of them apart based on mass. While they intersect. Do we need to do that? I mean, we do need to do that, but do we need to do that in that way? You know, we're just like testing it, and if it intersects with doing resolve collision, then we'd keep testing it over and over again. Just wonder why. Ah, right. Okay. I don't know. We're doing fine penetration, then we're doing fine separation. We're doing two different ones. I wonder why we're doing two different ones. Maybe there's two cases. Alright, well, we'll do this anyway. For now. is because it needs to happen multiple times, because it's going to get scaled by how heavy the thing is. Yeah. Okay. Yeah, I get it now. Alright. Because there's mass, they're going to move apart slower. Okay. Resolve collision. Where do we type that? Okay. So if they have no mass, what does that mean? So I'm going to go auto ma equals a dot mass a dot mass. If there's no mass, I'm just going to say it's 1. B dot mass and that's MA. This intersects AB, and this is A dot. This is B dot. Okay. B dot. So this is pushing the objects apart based on mass. Okay. So now we need to call resolve collision. Where is that? If auto pen resolve collision A B pen. If pen, sorry. Okay, so this is going to move A and B. move. It's going to try and move. Oh, see, that looks dodgy as. Okay. So we cannot now draw that. Alright, so let's just see what happens if we put gravity in. So, we'll change that. And then we'll put gravity in. Let's see if it has a reaction. We're applying a force at the moment. So let's just temporarily just add that force to the bounds. Nope. Gravity, of course, acts downward. It didn't fall through it. That's pretty good. Let's not draw it red either, because that was a little confusing. Where's that? That's in game state. Let's just continue to draw it green. Take that away now. Botneck, thanks for the follow. If you've got any questions, just ask. Just working on some rigid body physics stuff at the moment. There we go. So it drops. So let's just put it a little bit further this way. So maybe do it at like 9. Yeah, I'm making a custom engine. I mean, it's kind of finished. I'm trying to make a game with it at the moment, but there's not much physics in the engine, so I'm just going back and I want to put in. So I'm putting in mining, like gameplay, where you can mine for resources using like a laser, and I just want some rocks that'll break apart when you're mining. So I'm just putting in some physics stuff for like rocks to break apart. Right now it's just, I've just put in like a little thing that drops. No thanks. So the rigid body physics I'm putting in is I obviously want things to be able to break apart, fall apart, and and I want to put in rotation so they'll fall apart and rotate. Like right now there's no rotation. I've just got this square falling on this other square at the moment. Just testing it out really. It's kind of sliding a little bit weirdly.
Yeah. It's still nice. That's alright. It's still nice to talk.
But at least it's not going into the quad.
Yeah.
So I might just slow gravity down as well.
Yeah.
And this is actually a general collision detection algorithm, so I will be able to use it for not ordinary collision detection as well. Even though I've already got ordinary collision detection in the engine using a different algorithm. I just slowed gravity down a bit so we can see it a bit better. So obviously you want the green square to rotate. And let's not put like, let's make the mass like 10. Is that mass? And we'll see what happens to that. So say it's not like infinitely heavy. So it does push it down a bit, which is what you want. So we put it at like 2, so it's twice as heavy as the other square. It should have quite a big effect. Cool. Now there's no inertia, so it just immediately stops moving when it's not under any force. But we'll put that in. Alright, good. So we need to do this GJK one. I wonder why we do both. So we find the penetration and then we do GJK find separation. We obviously need to do it for some reason. And then it resolves based on the separation as well. Alright, well we'll put it in, and if we don't need it we'll take it out. But I'm going to put it in because it was in before. Alright. So it's just the two rigid bodies. Find separation. rigid body B. And let's just stick this code back in here. So it's a GJK separation result. What does that look like? Closest point A, closest point B. Alright, got it there, look. And we have whether it succeeded. We'll leave that in for now. I expect we can get rid of that. So we're going to do standard optional. Right then, so I'm just going to put this on a new window because it's only reference. So is it 0? That doesn't make sense. Like we're setting it to be not 0 and then immediately testing it's not 0. We don't need to do that. So vec2 D is not 1. Auto so I'm going to rename these because this is very A equals, this is very there's lots of single letter names. RA, RB, D. D equals minus D. Auto B is get the Minkowski difference. RA, RB, D. D equals geometry closest point along line to origin. Closest point along line to origin. B dot P, A dot P. And then we want the Minkowski sum point, which I've called C. These are bad names. Okay, so D equals minus D if D.length squared is less than the small float, break. C equals get Minkowski difference. A, B, D. Well, R, A, R, B, D. If contains origin. So that's the simplex. We only have that written in the simplex. So we need contains origin. Which is just a straight up whether 3 vectors contain the origin. Okay. So that can go in the maths library. And that's A cross B. B cross C. C cross B. And these are doubles. That's not right. Okay, so we can say if geometry contains origin, A.P, B.P, C.P, break. Found it. If C.P dot D minus B.P dot D is less than the small float, D equals D dot normalize result dot normal normal is D, result dot distance equals minus C dot P CP dot D. GJK find closest points. So what's GJK find closest points? Right. Alright. So I'll just copy this over. Alright, this is just straight up. Is 0. So if BM fabs L.x is less than small float and BMAbs L.y is less than small float, L minus L.ap Alright, see if that compiles. Okay. Find closest points. A, B, result. Then we can break after that. So auto P1 equals geometry closest point along line to origin A.P C.P if P1 dot length squared is 0 or is less than small float, return result. Well, it didn't pass, so we return a standard optional GJK separation result. Auto P2 equals geometry C.P B.P. So that is a fail condition. Oh, this is complicated. P1 mag equals P1 dot length squared P2 mag P2 dot length squared. If P1 mag is less than small float, Okay, so actually, this is if it is exactly 0, which is very strange. Suppose you got to cover it. So if P1 lag is less than small flow, D equals D dot normalize result dot normal equals D result dot distance equals P1 dot length or just BM square root P1 mag. Find closest points, AC results. Alright. Else, if P2 mag is less than small flow, D equals D dot normalize it's basically the same. So this is P2 mag and this is C to B. We can break after each of these. If P1 mag is less than P2 mag, B equals C, D equals P1, else A equals C, D equals P2. If not result, interesting, so we always find a result. Not always. Okay. C.P.D. Okay, so we can test this now as well, because I'm not sure why we're doing both. I'm not sure why. Where are we? Where are we? So we're finding the penetration and resolving the collision, and then we have to go if auto equals find separation AB I mean, is that to pull them together? Then we have to call resolve collision on the separation. So there, we're resolving it on the separation, which calls this crazy evaluate function. Ah, this is, yeah, alright. This is actually doing the spinning and stuff. Alright, let's just copy straight up this evaluate function because this is mad. Alright. Rigid body A, rigid body B. Separation point A, separation point B, N. Whoops. N changed at all. No. So that N and that N, I'm just flipping them. Okay, so PA bound, PA dash needs to be PA dot or PA dot PB arrow is PB dot. Call it RA. And call this RB. So the local center of mass, I'm not using, this is just center. Yeah, so we do this step now because this is going to do the spinning stuff. Vr.n. So it's R1 cross N. And this is R2 cross N. Okay, these can all be auto. This is vr.t. this is R1 cross T. And this is R2 cross T. And this is R1 dot cross that, and this is R2 dot cross that. So this is going through. So what's it going to? What's it doing? It's calculating velocity for each rigid body based on the old angular velocity. And then it's calculating, then it's incrementing new velocity, and it's changing the new velocity and changing the new angular velocity. So this is just the velocity. So this is evaluate velocities. Evaluate velocities. So you just cross. Okay. So we can change this up a bit. We can just say if denominator is 0, return false. Denominator. If denominator t is 0, return false. All right. So evaluate velocities. So this is now called evaluate velocities. A, B, SEP, A, SEP, B, SEP, normal. And that will change angular velocities and ordinary velocities. Okay, so let's just check that actually is correct. AB, yeah, that is it, that is it. Right. I'm going to set this to build, and while it's building I'm going to take a quick 2-minute break. We'll be back in 2 minutes. Right then.
I need to start doing some work.
Okay. Let's get a bit of food. Alright then. Right, so after we resolve these velocities, we can do this update rigid body with DT being the step. Is it the step? It's the actual DT. Interesting, we don't do it with the step. Nah, it surely has to be with the step. Right. So we're just gonna have void tick float DT. All right. So the local center is just bounds.width height over 2. Width height over 2. The force is the force. Which we aren't using. We aren't using R or F. So this is if the bounds ever change. Wait, we'll keep that there. Angle is undefined. We need that. Oh, it's called radians, that's why. Move towards move to. All right. Straightforward. And then we just want to do a.tick t b.tick t. All right then. Let's see what this looks like. This will either work well or it won't work at all. Not at all. So let's see. So there's no separation. There is a separation. So let's check if we ever get here. We do. So we are actually changing the radians value a little bit. So let's just log the radians value. B0.radians. It does change, just not very much. So we don't need to do this anymore. So we're looking for the green square to spin. Right. So the force. So I think this always has to tick. That's what it is. So it's moving very slowly. They're both falling. Oh, and the spinning, look at that. That's really good. So obviously we don't need to times it by t there. So the force is mass times acceleration. Right, so when we add this force, we tick. I'm just going to add it here. If mass is not equal to FLT max, acceleration plus equals, or acceleration dot y plus equals gravity minus plus equals minus 9.8. F. Let's try that. So now we need to set the mass to be actually FLT max. That's awesome. It seems to be going quickly though. Maybe, maybe not. Just set the gravity to be 3 again. So how often is this tick happening? Simulate pair internal. So this tick. Yeah, that's correct. That's correct. That spin the wrong way. It's difficult to say. Shouldn't it have spun? I don't know really. Okay, so let's just slowly, what we'll do is we'll just slowly spin this. B1.radians plus equals t dt times not, well, that's probably fine. Well, no, that's 1 revolution a second. So let's do it 10 seconds for 1 revolution. Uh, 2 pi times dt. Maybe like 5 seconds. That looks mint. That's... Do you want to see my physics, Dad? Do you want to see my physics? Come and have a look. You want to watch it again?
Alright.
Just those two things interacting together.
Well, that's really clever.
Yeah.
If you like.
Don't quite know if it's right. You see, it looks okay.
Well, as long as it looks good. Well, it's easy with a circle.
Yeah, easy with a circle, yeah. It looks a bit jerky as well. I mean, it's holding frame rate. So let's just do a little test then. Let's make a load of them. We'll make 10 to start with. So array make an array of rigid bodies, right? Bodies. And then we're gonna go for I to 10 bodies dot in place rect. So we're going to spread them all out on X. So we're going to go BM dynamic random between 0 and 10 in X, and then we're going to go BN dynamic random between 10 and 15 in Y. And then the sizes are going to be BM dynamic random between 0.7 and 1.2 2 times and then the masses are going to be dynamic random. We're going to do between 0.6 and 1.2. And then each pair needs a GJK. GJK.
Just got to run you through it.
Alright, yeah. See you later. And then we're just going to GJK's dot in place. So each pair needs a GJK, right? Each pair needs a GJK. So that's for I to 10, or J to 10, or whatever to 10. So 100 GJKs for 10 particles. So we're going to go X to 10 for Y to 10. So the GJK index equals Y times 10 plus X. So the auto GJK equals GJK's index. And then you want to do GJK simulate pair bodies X bodies Y. And then you just want to go through all the bodies. And just draw it. That's B dot bounds. B dot radians. So we need then to in place the ground, which is this, and then we need 10 more, because each one of them particles has to interact with the ground particle. So this is going to, so we want to say if x is y, we don't want it to do it with itself. Okay. Let's see how long this takes. This is a lot of computation. This is definitely going to have to be multi-threaded. Later. Get this working first. What does this look like then? Crashes. It crashes. 110. So 10 times 11 plus 0, so we're missing a row. It's probably that. Crashes, still crashes. Right, well, we'll just do this. For auto, for X in bodies, for Y in bodies. GJKs dot in place. Cost is only actually needs to happen if bodies dot get count is 0. Right then, compiled. Got 11 bodies in the system. So let's just not simulate them for now. See where they are. Where they all are. So this is testing body 0 with body 1. Okay. So the ticks, I believe, have to happen here. B.tick. Look at that. There we go. Let's just stop this debug drawing stuff for now. Whoops. And we just want to say, so the last one we add in, we'll make it the first, well, we'll make it the first one. And then we're going to draw 4B or 42B1 bodies. So we're just going to draw the first body onwards. And then the 0th body, we're going to just draw yellow again. Whoops. Bodies B. So the last one, so the first one, sorry, we'll draw it yellow. Bodies 0. Okay. Awesome. So let's what we're going to do next. I'll put a reset in. So we're going to go if window, get game window. If auto window equals canvas dot get input window, input window, I'm going to say if window dot key just down K, I'll say it's K for kinetic. I'm just going to do bodies dot empty gjks dot empty. I'll reset the system when we press the K button. That didn't work. K didn't work. That's very confusing. Key just up. It's a little sketchy, innit? Why isn't K working? try a little K. Let's try and figure out why the K isn't working. That's very strange. Key down. Okay, so we had an input key, we had a down key, window is 081E, so let's go back to here. Window is null. Do we not set that? Oh, it doesn't have an input window. Okay. Probably just don't set it. Game initialize. App initialize init. So it's just game window set input window. Never initialized it. Oh, sorry. Game canvas. Get game canvas. Set input window, game window. Alright. So now we should be able to reset. There we go. It's a bit jumpy. Let's time it as well. So do scope timer. See actually how, well, it's quite a lot of calculation going on, so. So it's taking 0.2 milliseconds in debug build on an old PC. It's a little bit like, if it gets into it, like, whoa. Sometimes it jumps around a bit. So the way we would So the whole point is to be a rock that breaks apart, right? So the way that we get that effect is X and Y roughly have to be the same. So we'll say between 9.8 and 10, and then the Y will say be between 14.8 and 10. So they all start off from roughly the same position. Oh, that didn't work. Let's just auto bounds. What's going on there? Why is that not working? The X and Y should be almost always the same. Okay, so let's just stop simulating a second. So they are almost always the same there. Oh, that must be a bug. Must be some typo somewhere that's doing that. So they're all on top of each other. Yeah, no. Oh, I know what's happening. It's spreading them all apart. Yeah, the simulation is like they're all on top of each other, so it spreads them apart because they all react with each other. So we can't start them off on top of each other. or we can only, or we just simulate it with 0. Let's try that. So we don't simulate the green particles with each other, we simulate it just with the ground. Should be a lot cheaper to run. Yeah, cool. So what we want to also do is it kind of needs to be right at the X location. It needs to be at about 5, so we'll do 4.9 to 5. And then want to make this first one a lot smaller. We'll just make it 1, 1. We'll make it go from -0.5, 0 to +0.5, and then those can go from, that can just be -0.25. 25 to plus 0.25. Cool. And we'll put it at like 8. We'll put it at 10. And we'll put the Y at 10, so we'll put them at exactly the same height. Maybe it has to be at like 9. Oh, hang on, that's the wrong one. Yeah, we'll put that at 10. Put that at 9. So they are all falling off. I want them to fall over both sides. Cool. So we'll put them a little bit more above, like 12. And then we also want to add a ground. We'll say -100 to +100. No. So it's -100 0, 200, 1. Like that, and we'll simulate with both the ground and the little diamond. All right. Should push the ground down. So the ground needs to also be FLT max in mass. So there's nothing to stop them. There's no friction yet. That one got stuck, look. So what I might do is have another key. We're just going to do static bool sim is false, and then we're just going to go if sim and then we're going to go else if window dot key just up. We'll say L. Sim is not sim. So we can turn the sim on and off and reset it. So we need some friction. So if it hits something, it has to lose some energy to stop them just sliding off. That's right. So what is that there then? Oh yeah, because I have to be 2. So now if I just press S or L, that stops the simulation. Let's B1 radians as well. So I might generate these a bit different. BM dynamic random then we might just say we'll generate them. Basically between minus 0.1 and plus 0.1. And the y is going to be plus 10 or something, and then this is just going to be p dot inflate. It's going to be rect p dot inflate dynamic random 0.5 to 1. No, 0.25 to 0.5. Alright, so that means it should be right over the top. Yes. So what happens if I press L to start simulating? It pushes them out immediately, so they need to be up a little bit more. 11. Oh, not that far. 11. So if I was to start simulating, so let's put gravity up to full strength. No, that was in rigid body, wasn't it? So the next step is we're going to have to be able to texture texture these squares to make them look like rocks. Well, no, next step is to put we need a bit of friction to stop them like sliding along the floor. So every time a collision happens, you have to sap energy out of it. So, where are we adding the forces? Okay. So velocity. So what I'm going to do is I'm going to put in a energy. Like that. And then basically velocity has got to tend to 0. It's got to be multiplied by the energy. And then all we're going to say is that energy equals BM saturate energy. So energy can't go it exists between 0 and 1. And then we're just going to go energy minus equals dt. No, we'll say we'll saturate it, and then we'll go energy equals BM not neg energy minus dt. So it'll take 1 second for it to run out of all of its energy. If it doesn't, no. Energy is so we'll do energy plus equals force times dt, the length of the force. Yeah. And then we're going to say we could say acceleration. So we need to put energy into an object when it's accelerating. Where's the best place to do this then? Because it's always under gravity. Yeah, I'm not sure. So they're not losing energy there. Hmm. So if you do simulate, call evaluate velocities. Let's have a quick look. So on the friction coefficient, really, where to put that? Jesus. Why is it all on one line? Oh. No. As a direction to the contact normal. Okay. So we have our contact normal. So let's put friction in here then. Let's not do energy, let's do friction. So this is orthogonal to the contact normal. So let's just go friction coefficient equals RA dot friction plus RB dot friction times this must be it. So just put a number in there now, like 1, and see what happens. There we go. They're obviously jumping around because they're not losing energy. So we do need the energy. We do need to make them lose energy. So So the energy is obviously half mv squared. We have the mass and we have the velocity. So we've got angular velocity damping. Set that to 1. So let's have a look at some of these velocities. So what is that state there? So the gravity is being applied all the time. Is it going down? So I think if we mark it as ground, we can just sap the energy out of it. If we're touching the ground. So we can say so we can put in energy. And then we're going to go if RA dot mass equals FLT max, RB dot energy equals BM move to RB dot energy 0 based on T. Well, we can't do that there because we don't have T. If RB dot mass, if yes, RA, oops, if A dot mass, then we move B's energy down to 0. If B dot mass is FLT max, then A dot energy, we move A's energy down to 0. And then when we evaluate velocities, we just do RA dot velocity times equals RA dot energy, and RB dot velocity times equals RB dot energy. Okay. So I think we're actually going to have to mark in what is the ground. Let's see what happens. not quite, not quite. So if we want to mark in what is the ground, well, hang on a second. So if that has to be times energy as well. And then we need to mark in what is ground. If we mark in what is ground, we can just say bodies not dot energy equals FLT max. So grounds, we'll just say that grounds have infinite energy, which is not right, but it doesn't matter. And then we'll say if the energy is FLT max, or that energy is FLT max, alright, so it disappeared, which is not the best. Why did it disappear then? Well, obviously got some kind of divided by infinity or something. Yeah, I got infinity. So let's just not do that. We'll just say we can only accelerate by the amount of energy. Right. There we go. So they did all stop. Oh no, we're hanging. So we're going to say if A.energy is 0 or B.energy is 0, return false. Okay, they did calm down. So if this is just 0, if we've got no energy, we can just do it here. And probably want the energy to dissipate a bit faster. So it seems to be dependent on size as well. I was going to say 5 times faster than that. Oh, that's crazy. See, look, it's still got. So we do need to evaluate the velocities. Let's try that. And the radiance has to be dependent on the energy as well. That's pretty good. Dr. Elliot, hey, how's it going? Welcome back. Just working on some physics stuff. Just implemented this. It's not quite right. It's nearly right though. It's meant to be like you blast a rock with your mining laser and it falls apart and you'll be able to go and collect all these things. These are a bit like, you know, ore. So if we just don't draw the body, don't draw the floor, don't draw the thing that makes it break apart, and see how that looks. So the floor needs to be a lot closer to the actual body. So we'll say the floor is like 8. So you come up here and you blast it. Oh. These need to be a bit smaller, that hung there. Make it 7. So you blast it. So we'll say 7.9. So I really want it to just fall apart. I don't want it to look like it's falling. Oh, come on. So that's making it hang for some reason. So let's just make gravity quite a bit stronger. And then let's make the thing that it crashes into to break it apart quite a bit smaller. Missing it there. Let's go back to drawing them. Oh yeah, because it has to be on 0. I want to just make it look like it just falls apart, not like it drops down, hits something and falls apart. Okay, so that needs to be up. So where are these coming from? 11. So let's just put that at like 9. So they're on top of it, which is not right. 10. Get this looking alright, and then I'm going to have a quick break. Make a cup of coffee. It's good though, we got the rigid body physics working. Alright. Oh. Let's try that again. Hot load didn't work there. All right. So let's just do 9.5. There we go. So let's not draw those again. Come on, we shoot it. Breaks apart. So let's make them a little bit smaller as well because they're quite large. We'll go 0.5 to 1. We are getting it. It's locking. Figure out where it's locking. Does it ever get out of here? Never get out of here. So is it in here? Does it ever get out of here? No, so it's locking in here. So let's just strictly say that's greater than 0. Awesome. So let's just make more bodies. Let's see how it copes with 100 of them. This is a lot of work to do on one thread. Not too bad. Takes about a millisecond. We need kind of like different sizes, a little bit more different. Yeah, so maybe we'll go up to 0.2. So millisecond's pretty slow. Shoot it. Pew. This kind of looks like fluid. Let's try 64. I mean, we won't mess around with this too much. The system works. Things can break apart. Next job is to actually texture all these. Next job's to texture all these to make them look like a rock. You stress test it. Let's give it like 1024. So this might take like 10 milliseconds. Still going as well. Very fluidy. Let's try 32. So I also think we want to do is add some random force to make them kind of radially go out. You can go and collect all them up. So it's like a shooting it, and then the rock image disappears and it breaks into a bunch of rocks, and then you can go and collect them all. It's quite nice, really. So let's also make them not completely opaque, because then we can see rocks laying on top of other rocks. And then we can kind of give it a grey rock colour. So we could like shoot a rock and then have a particle come off the rock and hit the rock itself and then break apart like that. Yeah, I could do that. Let's make it kind of grey. Maybe quite dark grey. So we could have a rock and then we could place these things on the rock, and these things just, when the HP depletes, they just break apart like that, and then you can go and pick them back up. That's probably what we'll do tomorrow. We'll do something in Photoshop and then we'll put like a little point where we want these little break apart things to be on the image, and then they just break apart like that. So we also need to know when the system is finished. So we need to get the total energy of the system. So we need kind of an idea of a rigid body system, because when the total energy of the system is gone, we can stop simulating it. So we need to do that as well. Maybe we can do that now. It's quite a nice effect though. And also, we don't need them to be quads, really. I mean, we probably will have them as quads, actually. I don't know. We can make them actual rock-shaped. Quite liked it when they're a bit smaller, actually. Let's put a little explosion in. So play the effect control and play effect strike 0 effect. So this is if L is down. So let's just do vec2 position not 9.5 9.5 position.x, position.y. No, that's not right. Where is it? It's 10, not 10. Plus position.y, and this is plus position.x. And then we're just going to go, if you press K, press L, if sim, get effect controller, play effect, and what does it look like again? Canvas, strike naught, position. So that just puts a little explosion in. And we'll see what that looks like with a bit of an explosion as well. Include effects controller. Obviously this effect control, this strike naught effect isn't really for striking in midair. Oh, that's the lightning strike, that's not what I wanted. Which one was it? It's an impact effect. Impact. So it's framed animation effect. Impact. So it's framed animation effect effect type impact. That's what we want. Okay. That's cool. So obviously the impact timing is a bit wrong. So how do we set the timing up for that? Okay, so let's just do position minus vec2, and we'll just push it down a bit, 0.2. I mean, I won't mess around with this for too much longer, actually. Because it's kind of ready to go on to the next stage. So I think when I press K, I want the sim to reset, and then I need to go sim equals false. And then I might just get it, let's just work on it, just get it to see if it looks good for a second. So static alpha is 0. And then let's just do alpha times that. And then if sim alpha plus equals dt, and saturate it, and then we just want to go if alpha is greater than 0.1, 0.6, else 1, else 0, sorry. So it's greater than 0.2. So we make it come in a little bit later. And then we'll reset Trying to get a feel if how this is going to look really, because I don't want to work on anything more today because my brain's a bit fried. So if I press L, look at that. That looks like rock breaking apart. If we had that on the side of a rock, piece of artwork. Awesome. Alright, got 5 more minutes to mess around. And we'll call it a day. Let's give them let's give him a, let's just try and give him a little bit of force. Bodies. Force equals BM. Because force is a vector. Yeah. Dot X equals BM random. BM dynamic random. Minus 0.1 to plus 0.1. And then let's do the same for Y. Oops, I don't know if actually if we deplete the force at all. That's not very strong. Just give it a ridiculous, like a big amount of force. Don't know if it's even doing anything actually. Oh, it is doing something. Maybe it needs to be bigger then. Like 5. So let's make the force on the Y go from 0 to 20. Let's try and shoot some of them up into the air. Like it has to overcome gravity. At least for a bit. Well, they're really going off. Let's make them a little bit. Because the force, we don't ever actually do anything with the force. So let's just set the acceleration. Got immediately overwritten. We don't have an acceleration. So I think that's like force.y. Let's try that. Okay. So force. Let's just times it by energy. Let's see. Some of them go like properly off. Let's go back. And let's say that that is force.y. Yeah. Interesting. I think I would like to have some of them go up a bit. Obviously not like that, that's crazy. It's because the force needs to be depleted. Force.y equals force.y minus 9.8. times dt times dt. So we'll gradually remove the gravity. We'll gradually let the gravity take over. That's kind of cool. We need less. We need more gravity, maybe. That's quite cool. So I think we want more force for the smaller particles. So the force, we're going to say divided by bodies index.mass. We'll say bodies index.force divide equals bodies index.mass. So the bigger the smaller the mass, the bigger the force. Yeah, I don't know. So we are already dividing force by mass. There, just take that out. So what can the masses actually be? What are we setting masses? Between 0.6 and 1.2. Yeah, so the mass actually has got to be dependent on its size, I think. So bodies index dot mass equals that times bounds dot area. Or we could just make it its area. That means all of the smaller ones will fly up. Whoa. That's way too big. Let's just make it 1. Some of them are proper shooting up really high. So let's just do 1 plus. At least has a mass of 1. All right. So now we can go 5, 5, 20. Let's just go back to where we were. Giving them such high velocities. Yeah. $10, not to 50. Okay. So if we go 20, 5, 5. So somewhere in between that. Let's try 8. 8 day. That's quite cool. Some of them get quite far away. So maybe we'll pull that back a bit. And then we need to make them react with the other rigid body physics, the other collidables in the world, I think. That's cool. Alright, so I think we've got ourselves the beginnings of a crumbling rock. So we're going to be able to shoot our laser at the rock and it's going to go pew, and then we'll be able to go and collect all these little pieces. And that would be like iron ore or something like that. And it's nice because it's proper physics, it's different every time. Cool. Alright, I think that's me done for the day now. So I'm back here at 9:30 in the morning, tomorrow morning GMT. See you later.